work never included how you decide when you get a function in the direction. That was entirely up to the directive already. And never included any of the logic about how you decide about those lines, and that's up to the final test. You have to start with the probability. So, as far as I know, there's room to come up as you want with SSC funding, and it will work. You only need. There is but currently I don't see a need.
Okay, it's 9:30. Let's get started. Good morning, everyone. Welcome to the RTGWG session, and stay until Friday for this session. I'm Ying Zhenqu from Future Way, co-chair of RTGWG, and I have Jeff Tansara, my co-chair, online with us. So for today's meeting, okay, this is not well. I think by now everybody have seen this multiple times this week, hopefully. And this is the agenda for today. And anybody have any questions or comments?
David Lamparter. I don't want to really discuss this, but I believe the BGP blockchain draft does not have sufficient merit to be worth our time here. So I would just like this to be recorded for future sessions.
Okay, points taken. And here is a link to our RTGWG wiki. You can find some latest information about working group documents there. If you have any question about RTGWG, you can always send an email to the list or send an email to the chairs, and we'll provide information as soon as possible. Right. That, one more thing to mention. So now we have a new routing AD for RTGWG. We should thanks Alvaro for his leadership over so many years, but he's now here. So but let's give a welcome to Jim.
Hey, Jim.
Okay, Dirk, you are the first presenter, I think. Which one you want to go first? The ROSA or BGP? Which? Up to you. You want to control? You want to do the ROSA first? You don't. You are doing. Oh. You don't do share. I do share, and then I will pass the control to you.
I'm sorry. Yeah, it does sound different now. Reading on service addresses, as you can see, Dirk Trussen, Huawei, and at least we have one of the co-authors, Luis, is in the room as well. Jens and Paul, I think, are online. It does work. Good. Goal of this draft is to provide an alternative, not a replacement, to DNS-based service routing through an in-band on-path service discovery. It provides transaction affinity. It supports multi-instance, and in particular in highly dynamic and highly distributed service scenarios. And we outline in the draft, and in case you have looked through it, an argumentation, motivation, use cases, benefits, requirements, a possible solution. So to ground this into something of how you could do that, subject to discussion. And also we outline a possibly wider body of work and are working on insights for feasibility. The section is at the moment still empty. We presented this in IETF115 in London already. Changes since are mainly in the first 9 sections that are shown in bold. We added our 2 co-authors, Paolo and Jens. Since then, we restructured the introduction to improve readability, argumentation to the draft, changed quite a bit. Also based on comments we received at and right after the IETF in London. In various parts, as mentioned, introduction, we added an analysis, we added the relation to Anycast, there were questions around how this relates to ICN, et cetera, et cetera. I addressed the various comments received from the community, listed the names here. Many thanks to those that sent mainly direct emails to me and exchanged, was very, very useful. We added a number of use cases, 6 new use cases in total. I'll get to them in the next slide. I listed them here in the various sections. Separate analysis section, as I mentioned, that's derived from the use cases that look across the use cases. I also have that captured in the next slide. We link the requirements to the use cases better. So the requirements don't only read like requirements. They actually have references back and forth to the actual use cases, which should help. We discussed possible benefits for the approach that we are proposing, and very few changes only in the actual more technical part. I mentioned the possible solution, just a couple of revisions to the figure, the messaging figure, to make it better readable. We also added, in reference to what I mentioned before, extended capabilities. If you had a base capability like Rosa, what it is you could be doing on top of that. That's the new section 8. Also, again, based on feedback that came from our co-authors and the community. That's one of the reasons why Jens and Paolo joined as well. We added and maintained open issues, which hopefully allows you to trace the changes a bit better. And we also added missing sections that I just forgot to do the last time at the end. Okay, my errors disappeared. They're back. Good. As I mentioned, the use cases have been extended. The italic ones are the new ones we put in there, coming from various parts and the co-authors, and spanning things like CDN interconnect, but also mobile applications, video delivery, VR. We have the M word. We have a metaverse section as well. How could you not nowadays? We have one actually we carried over, and there's a reference in the draft from the BBF efforts on metro compute networking. It's the last one, the popularity-based services. We really tried to spread this quite a bit. We then did the analysis, the right-hand side. This was initially in the PowerPoint. This is animated. So the right-hand side on the draft here is the highlights of the analysis, which is now in section 4. That is about the separation of application and routing namespaces, where the additional discovery needs to do the mapping. We have some text on this. The Anycast problem, which is a service Anycast problem, not a packet Anycast problem, when instances reside in more than one location. The ephemeral lifetime of an instance, so the shooting up of instances fairly quickly, that's captured, for instance, in the microservice-based mobile application use case, where instances may appear in network locations really, really fast. Dynamic service instance selection, highly dynamic instance selection, as well as the latency budget, that's very often an issue. And the dependency across service invocation, which leads later to discussions in section 8 on the capability of chaining for instance services. The key benefits are then pulled out of this in the section 6, which is the support for the high dynamicity, the service specificity of decisions. So the decision you're taking in the selection is very often highly dependent on what service you're looking at. The reduction on the DNS of the DNS dependency. You may still have DNS-based services. For a lot of services, this solution makes no sense. You're talking to your bank. stick with the DNS. There's no reason to use Rosa. There's not a lot of dynamicity there. We don't assume that you're hopping between instances when you do bank transactions. But for some of the services, it's very, very useful. Higher service distribution, I already mentioned, when in particular in edge computing type of scenarios. And the protocol support, which comes out of a piece of work that's being referenced from BT and others on a protocol support for automating the mapping of the namespace onto the communication namespace. Okay, so the main idea for those of you who haven't actually read much on the technology side, as I mentioned, it replaces in those services, not generally, not for every service, but for those services that you decide to run over Rosa, the DNS plus IP sequence, which means the off-path discovery of a service name to the IP locator with an on-path discovery of the actual instance that you would like to choose. Now, you send an initial IP packet, it's directed, and this is put in air quotes because the actual destination address is still an IP address, but it's directed to a service address, and it's being sent to a special shim overlay. The shim overlay routes the packet based on the service address. It makes a decision among one of the possibly many service instances that are being deployed in the network for the particular service address that's being given in the packet. You may cross several IP networks when you do that, so it's inherently cross-domain, and uses mappings that replace the role of the DNS records, if you will, but they're closer to actual routing table lookups. Actually, we use in an implementation eBPF what's typical routing table, so it is actually a routing table, if you will. And it gives you the actual service location, then it delivers the service instance location of, meaning the routing identifier of the selected instance back in the packet to the client. So that's your in-band discovery that I mentioned, and it then uses for any subsequent packet the service instance locator directly. So the shim overlay only routes the initial packet. Everything else is shot directly between the IPv6 addresses of the client and the service instance. You repeat this for every service transaction, and the service transaction is entirely delimited by the client. The client is the best to know what is the actual boundary of your transaction. And a transaction, we mean, is the semantical unit that lets you speak with a particular instance. If the transaction is over, you go back to step number one, and you may be directed to another instance of the same service because now you are in a new transaction. There's no ephemeral state between these two transactions, and you can be directed to another instance. If you are within a transaction, you just keep sending in step number 4 using the IPv6 address because you have ephemeral state. You should stick with the instance and you shouldn't go out. The key point is the in-path discovery is performed at IP level. So that initial packet in number 1 has already payload of sort. For instance, I don't know, your handshake for transport security, right? Could be in the first packet already. The service response has payload as well, and then you keep sending. So that's where the aspect of in-band discovery comes in. Sorry, I have to wait for my cursors, my arrows to come back. Okay, there they are. I'll skip this part, the recap, the system overview. They're in the slides, you can look through it. There's a short summary of what section that's now moved to section 8, I believe. It's given, so it's layer 3.5. We use extension headers. In-band discovery I mentioned already before. There are different modes described that either allow you to do an instance selection right at the ingress or to use overlay routing. It depends on your service, and sometimes it's better to do overlay routing, or you do direct ingress selection, ingress-based selection. That depends on the service as well. And we have use cases where we do either. Right? How is instance affinity being done directly over native IPv6? It talks about the limitation of the table size. There was a very good question after IETF116 saying, doesn't this smell like ICN? Yes, it does. I've done ICN stuff for many, many years. The routing table size is limited by those services being announced to the Rosa domain, however. So you may have very, very specialized Rosa overlays, for instance, in some of our use cases to gaming or edge computing. Try to ask, how many edge computing services an operator would like to support, maybe a few hundred. And we've run this already in prototypes with 1 million service addresses at no problem in terms of performance. So the routing tables here are relatively small. We're not talking about routing on every possible name in the internet. That's a very, very difficult problem. It's not the same thing here. It doesn't require client awareness. The client can send to any address. If that address happens to not be in the domain, we have a mechanism that's explained in the draft of how this goes out in the internet. Right, and it uses traditional DNS to do that. What are possible extensions? Skipping, that's actually, so sorry, the previous one was section 7. We changed the section so much that I forgot the section. Section 8 is the new section we added. What is it you could do if you had a base capability? So what's described in the section before. You could use different namespace encodings. We very often draw these slides and write on it foo.com, service.org. So first of all, we're not putting URLs into the packets. That would be stupid and dangerous. But it's just for you to understand that we're talking about application namespaces, right? Just for visualization more than clarification of technical side. There are different ways to encode namespaces. There's a discussion section 8 of how to do this, to rely on our C8066, which is what we are doing in our prototype, to use maybe a DNS-based one, a hash-based one, etc. And that has different pros and cons that are discussed in section 8. Also important, you may not have any DNS or any URI-based namespace at all. I had a discussion with Colin Jennings about his work in Quicker, which is also something we are referencing in the use cases, where I may use an application identified as 128 bits compressed form of some group session, etc. description. We support this in Rosa as well. You have your own application namespace, fine. How do you do multi-homing? That's something that Jens in particular provided, and how to extend this to an instance itself being multi-homed, right? That's an interesting use case as well, or deployment case as well.
You are eating into time of your next presentation. Be aware.
Yes, sorry, zero RTT, etc. So look at those possibilities that are described in section 8. And that gives you an idea. What's the plan moving forward? We want to tighten the argumentation for work. So is this something, in particular discussing with the wider community, I reached out to a number of people doing the IETF here to make a better case for our argumentation, also the relation to other pieces of work, position against other related work that people may identify. More details on design realization. That's not necessarily our focus at the moment, because we don't want to push forward with our ideas on how you could do it. We just want to ground it somewhere that you could do something. Implementation insights. We also have plans to maybe come with a demo and hackathon of something that we realized. We wanted to do this already, but it didn't work out for this IETF, unfortunately, for different reasons. So what we seek is really feedback on problem space, argumentation, motivation, the positioning of the work, the approach itself. I'd love to have more architectural discussions. I had some really, really good discussion with Joel on this as an example, and I'd love to continue that. Any parties that are interested to possibly contribute to the discussion, please drop me an email or on the list, and then the way forward. Thank you.
David.
David Lamparter, you mentioned on slide 6 a destination header to add into IPv6.
Yeah.
It's not immediately clear to me where exactly that would be used. But since we're short of time, maybe just a hint for next time to present that part.
Yeah, I didn't want to present the technical approach too much, because there's a lot about how do we do the technical approach. That's section 7. Please look there. It should be quite clear, hopefully, where it's going. Right.
Yeah, IJ1 from Taiwan. Would you like to back to the slide 6?
As fast as I can with this tool. So bear with me.
Yeah.
Yeah.
In your diagram, I think every song must store the mapping table for the service and the locator information.
That's correct.
So my question is how you get to the how you populate such information within the among SRs?
So
in a traditional protocol or other you design new protocol?
We can use so the one that we're shortly describing or briefly describing in section 7 is a distance vector protocol. You can use any overlay routing protocol you want. We're not necessarily proposing to sticking this into BGP, because I hear people already moaning and screaming if I were to do that. It's information dissemination between routers. We know how to do that. So that's a choice we're currently still discussing, and also want to get feedback from.
Yeah, I think if every SON router has such information for the service and its locator. So can we moving further? I think the ICN RG working group also doing the similar things, but they do not depend on the traditional IP network. So I think if every SHA router has the service routing information, we can design such a solution independent of the IP technology. Maybe more resolution progress.
Yeah, as I said, I've done ICN research for many, many years, and I think one of the things that I did is moving away from revolutions. I know that sounds weird for people who know me, but I think the intention was to actually run this over an IP network. Because we want to run IP-based applications over an IP-based infrastructure, right? That's the reason why we're actually not doing this. We've actually done previously work that actually does IP and has ICN underneath. We've done work that does ICN and has no IP underneath. We've done this. This one was specifically aimed to run over IP networks because it's deployable. So it was a little bit the ambition.
Okay, thank you. I think we are very interested in this topic, so I think we can discuss later.
Yeah,
as well.
happy
Thank
to.
you.
Please take it to the list.
Yeah, so any list discussions, contributions, please do. I'm very interested in that. And it's also making it a wider exercise. I don't want to be the only one beating that horse. It would be good if other people join the wagon. Thank you.
Yeah.
I think we have to move to the other one.
Daniel, you want to make a quick comment?
Yeah, there's a
Very
quick
quick.
quick comments and about the transaction mobility, because the context word state will always to be maintained at the service. So I just wonder if there's kind of a transport protocol or application protocol involved to aid the mid transaction mobility.
Yeah, that's described in section 8. So it's not about the ROSA overlay doing transaction mobility, because that's terrible, because you have to have a lot of application knowledge, but to support transaction mobility. So I hope the text makes that clear, so that nobody starts shouting at us and putting application context into not the network, but even putting into an overlay would be really futile to do. Now it's supporting it, and both the actual traffic steering decisions, but also potentially the transport protocol that runs on top. So I hope that's been made clear if you read the section 8.3,
Okay,
I think. Thank you. Good. Blockchain for BGP. I'm still presenting it despite the comp before. And if that's the feedback that this shouldn't be presented here, then it's fine. This is work that, sorry, Mike, I think it's somewhere in the room in the back. I've seen him. Hey, David is probably online. Thomas probably as well. So the goal of the draft is really to review, and this is why we're presenting it here, right? Because it's ongoing work that's trying to find its place, review possible opportunities to use DCSs. I know the draft says blockchain. We have an ongoing discussion with Mike to maybe should we use blockchain or DCSs. I'm coming more from the camp where I'm calling it a distributed consensus system, and blockchain is an example of it. Propose that maybe data could be placed in the DCS and smart contracts could control how the data is being managed. That's an interesting application or a view of how DCSs are useful. Creating a single source of truth, that's something that a lot of network functions really need. And here specific in the BGP context as a complement to existing mechanisms like RI and RPKI. So we've presented this already, or intended to present in 115. Since then, we have several changes, also by adding another course, Thomas Martin, who's now part of the team as well. We added key challenges to be addressed. So when you think about using this in a network context, in particular in BGP, what are aspects that come from DCSs? And if you're familiar with DCSs, it has 3 key parts that excite people. One is the update latency. How long does it really take to propagate updates to the distributed state in a DCS? And obviously from a network function, from a usage perspective, that's really, really important. If I want to make an update to a routing table and it takes me 40 minutes to propagate that, there's a bit of a mismatch there, right? So that's why we are evaluating, or we have first text on that aspect. Costs, how much does it really cost? And I'll come to that in another slide. There's been recent work on looking at cost, and there's a lot of statements on costs for energy on proofs. Everybody knows that, getting excited about prime number crunching. But we are actually looking at the cost for communication. What is it actually doing to the network, right? And changing stuff around, working in consistent state. This is more related to the proofs, actually, so the third part is. We outline possible, and this may be of interest to the network community as well, to the routing working group, what could be network solutions that could help address some of those challenges. For obvious reasons that you may have seen in the previous slide deck. Routing on service addresses is one of the ones we're actually looking at. Can service routing in general help to address some of those challenges? CAS, the compute aware, the relatively new work on computer awareness, could this be helpful? We have also there a placeholder for Lisp. That's something we still want to fill up in the future. As a bit of background for those of you who don't node DCSs or blockchain too much. Smart contracts here are usually used as a term to describe programs realizing operations. In this case, our context here is BGP. So BGP-related operations and store the state in a DCS. So the DCS could supplement existing BGP management data as it exists. The smart contract then could be executed when some condition like receiving an update, et cetera, is leading to an unwanted conditions like too many prepends or hijacking detection, et cetera, et cetera. In terms of realization, a DCS is realized through a peer-to-peer network. It's entirely an overlay where participating nodes verify transactions, they execute smart contracts, you use concepts like boot nodes, seeding nodes to bootstrap clients, you process new blocks, you have full nodes versus lightweight nodes. So all of these concepts are in realizations of DCSs. The draft describes several opportunities that are outlined to use DCSs in the context of BGP, whether it is about avoiding fraudulent region assignments, validating incoming updates, routing policy updates, etc. Each of these subsections has text in the draft to outline this. And again, we're seeking their feedback from the community as to, are we overstating the opportunity? Do we know how to do this? Is there a room for improvement with existing methods? That's the point why we seeded this in this section. We're not necessarily claiming you have to use DCSs on those. That's why they're called opportunities. They may or may not materialize. The key challenge is the new one that I mentioned before. There's work on in convergence latency, as I mentioned before, the communication cost and the working in inconsistent state. We had a separate draft last year, which we decided not continue. Instead, we took it out and published more extensive results in a paper that investigated the communication costs and the latency. Communication costs in particular has very little done in the community before. Everybody assumes that doing stuff over a network, you don't have to care what you're doing. Actually, you should. If you investigate how Ethereum, for instance, worked, which is what we're doing in this paper, it sounds quite scary of what's happening. And it's a very, very significant communication cost that's being put on a provider network. That's all fine if you're okay with it, but it's good to understand it. I'm not judging that you shouldn't be doing it, but you should understand what you're doing. Right? And that gets us then to insights on convergence latency, which then, on the other hand, in the context of BGP, may also gets us to understand, is it at all useful to talk about using it if the latencies are in boundaries or within bounds that are just way too large for the application use case, here BGP. The working on inconsistent state, an interesting question, is that it's something we could even accept in certain application use cases, right? There's a lot of, so the lack of fast consensus that you have because of the relatively high convergence latency leads you to all these various sophisticated methods that exist in DCSs to work on this inconsistent states with the various proofs. And is that something that's acceptable both to the community, but also is it technically acceptable? It's something we started adding to this. Possible relevant solution, again, this is a routing working group. So we said, well, could there be something around in the routing area that could be relevant for this? The Rosa draft was presented before. So what we've looked at, we interpreted a DCS as a service environment. This is not usually how the code is being written, but you can redefine it that way. You have an insertion service, a diffusion service, and a query service for those of you who know how DCSs work. And could you use an anycast, a diffusion mechanism that is more network oriented in order to address some of the latency and cost issues that we identified in the section. Things around reachability and availability, which are the real troublemakers in a peer-to-peer realization, because you don't really quite know if your node is there, and if your node is there, maybe behind a firewall. All of this is a lot of the methods that are being employed in current DCSs are all geared towards solving that problem. Could be solved differently and more efficient if you actually would do things like routing announcements and aggregation. That's what we are outlining there. Computer-aware traffic steering, could you actually accelerate diffusion by complementing the routing approach by diffusing to in a compute-aware manner, so for instance to less loaded or well-connected peers? That's a bit quite debatable because it also runs to an extent counter to what you actually want in diffusion. You want to diffuse it to everybody in the system and not bias it by methods. So that's something to look at. But computer-aware traffic steering has at least or is geared towards developing tools that would allow you to do this. And Lisp comes through an interest that came from Dino, which we're still trying to get into into the document. Summary, next step. As I said, smart contracts are programs executed. BGP DCS, could use a DCS for distributed state information management. As I've been saying, could. The question to the community is, should it be done or should we not consider that? We have extended identified opportunities. We identified key challenges that are important when you do this. And we also looked at a first set of network technologies that may help us in all of this. What we need is more input from the wider community, in particular network experts that help to tease out the challenges better. These are possibly not the only ones that we listed. And also DCS experts to kind of like align our insights with the latest state of the art. There's just last point, there's a mailing list for those that are interested in this area on the combination of DLT and networking to just discuss these. Again, just to make clear, we're not talking solutions, we're trying to talk opportunities and challenges. Thank you. David.
David Lampotter. All of the 7 use cases you list have an existing authority, in quotation marks, that makes the decisions for these. It is completely useless, in my opinion, to try to stick distributed consensus onto that. You're talking a lot about diffusion and querying. Those parts could be useful, but when you remove the distributed consensus, you're not a blockchain anymore. And it's a very different problem. I don't believe this is, there is no purpose in this.
Okay, thanks. One quick answer to your aspect on the existing authorities. One of the things that we haven't discussed yet in the draft is the difference between a permission and a permissionless one. So you're more opposing a permissionless DCS than a permissioned one, because a permission one is potentially what you're looking at.
If it's permissioned, why is it the blockchain? Like,
again, look at it as a DCS. Again, we were going into the name discussion was one of the reasons why I suggested use DCS rather than a blockchain. Blockchain, people think about a very, very particular instantiation of it. Yes, sorry, I can't see the name list.
Q myself.
Yeah.
So you mentioned this as a possible single source of truth, and for that to have any cryptographic validity as a source of truth, you would have to have buy-in from the authorities which hand out these internet resources, such as RIPE and ARIN and etc. Have you had any discussion at all with these groups, and have they indicated any level of support whatsoever for what you've proposed here? Secondly, your security considerations section is 3 paragraphs, and as far as I can tell, mostly says it uses public key cryptography, therefore is secure. This seems extremely woolly and does not consider any of the security considerations of cryptography at all.
So the question, I think the general meta answer to what you said is, one of the reasons we are putting this here, we are not proposing a solution, we're not proposing a way forward, we're proposing to have discussions. So the answer to your first question is, we'd like to have these discussions. And the outcome may be exactly leave it, and then we're leaving it. So I don't really quite understand the kind of like the negative tendency of your questioning. The point is, if the discussions can happen, I'd love to see them happening. And if the outcome is better don't do that, then that is a worthwhile. What we're trying to do, and this is what a draft does, is to instigate a discussion, record the outcome of the discussion. If the discussion is negative, we will record a negative outcome of the discussion, but at least it happened and it is recorded. So I'm not entirely, if you feel you can facilitate those discussions, please help us doing it, and then we're doing it, and then we will record the outcome of it.
Okay.
Because that's how I understand the process of the
James,
IETF.
I would like to
unless
cut
you
it
misunderstood
here.
it.
Andrew.
Yeah.
Andrew.
Hi, Andrew Alston, speaking in my personal capacity. You're saying help you facilitate the discussion. So I'm going to give you a suggestion on how to facilitate this particular discussion. Take this to the IRTF, because to me, this is very far away from what could potentially become a standard at this point. I think it is very early days, and at best, I think that it is a research topic, and I think that the work would be better suited to the IRTF. That's my personal opinion.
Okay, thanks. That's good feedback. Thank you.
Rudiger.
Rüdiger Volk. Well, kind of, I'm not seeing a kind of a direction what you are actually supposed to tackle. I think this looks like a kitchen sink of problems that are raised once in a while around people who are using BGP. Well, okay, these look like very different problems. And kind of, yes, if you have a magic wand, maybe the magic wand makes work with magic. But I think in real world, magic wands aren't available. And magic is only very rarely available. So it might be more conducive to getting results and answers if you really cut down the various problems and investigate and tell how your magic wand applies to the specific problem. Talking about, well, okay, we have a magic wand for BGP, kind of the question goes down for me. Well, okay, what are you thinking about? Are you thinking you want to map the global BGP state? Nobody has done that, and I guess the fact that actually BGP only is available with a lot of network-specific vantage points is a part why it actually works, and yes, why there are, well, okay, it certainly implies some problems. Another point at...
sorry to interrupt. In the interest of time, can you please be brief?
Yeah, sure. I'm getting... if you go out and say, well, okay, we have something that's based on network-based computation, and that's going to help the routing system. Please be aware that you are actually going to depend on a cyclic dependency, which is kind of a very dangerous and strange thing to do.
Yeah.
Okay, thank you.
Yeah. You want
Dirk,
to
we would
go
appreciate
quickly?
No,
if
Continue the discussion.
I think
in
the best to take away is Andrew's comment. I think it's a very fair one. This is an investigation. We don't have the magic wand. We're throwing things together that we found in discussions with people out there. Want to understand how DCSs could be useful. We don't have a solution in mind. We look at a technology area and try to understand how it could be useful, or how could it not be useful, and it should stay away. So I take Andrew's comment as the best and most constructive feedback, and maybe carrying this to the IETF to see how we can actually make sense out of this. Everything else, I don't want to get people heated about that we're trying to push something. I don't think anything that we presented actually was pushing a solution. It was asking questions. Yeah. And if you can't do this in the IETF, then maybe I can save a bit of money the next time. Thank you.
Thank you, Dirk.
Dirk, thank you. And my personal capacity, I fully support Andrew's opinion. It's more suitable at this point in time for IRTF than IETF.
We'd really appreciate if people in the room can help with the note taking. Can use the hashtag. I'll send a pointer in the chat. And let's do the next presentation.
Good morning. My name is Tan Zhen. I'm from Huawei Technologies. Today I'm gonna do a presentation on the protocol assisted protocol on behalf of my co-authors. Next slide, please. So last time presentation on this draft is on IETF110. So it's been 2 years. I'm gonna do a brief recapitulation and talk about updates. So PASP or PASP is a east-west approach to gather and distribute OEM information. Next slide, please. So firstly, why we want an east-west assisted protocol? Why an east-west assisted protocol is needed? And now we have some challenges of the north-south methods. So if you have a centralized controller, you need to deal with a large amount of data, and therefore you're going to have some performance issues for gathering all the data from different devices. Also, for any AS, an OEM person will deal with deal with devices from different vendors, so there will be some user habit issues. If I am an OEM personnel, I have to learn a different set of interfaces like CRIs. So it takes time, and also OEM personnel need knowledge about various vendors, or even within the same vendors, there will be different interfaces. Also, we already have some east-west methods in use, like RSVPT, pass error, or a BGP notification method, or other protocol-specific error shooting mechanisms. Next slide, please. So why a general assisted protocol is needed? Firstly, if we have some built-in mechanisms for routing protocol, and the routing protocol is failed by itself, it's very likely it cannot advertise its own maintenance information, right? Also, we have some restrictions on the mechanisms of the existing protocols. So if we want to introduce more mechanisms about the maintenance, it will affect the performance, either in performance and complexity. For example, if we want to extend BGP for more pass attributes to carry maintenance information, and it will have some effect on normal routing, like parsing and route selection performance. Also, for multiple routing protocols, there will be common issues, like the interruption of the line. And if we have all the protocol-specific maintenance mechanisms, we have to do the protocol extensions one by one. So next slide, please. That's why we want to introduce a protocol-assisted protocol. It's a general approach, a semi-distributive and a semi-centralized approach. So I say it's semi-distributive because we don't have a centralized controller. It's semi-centralized because we want to gather maintenance information on one device. It's like a generic pipeline for exchanging troubleshooting data of various protocols. And it's designed for exchanging protocol-related information between devices. By doing so, we're going to have a lot of merits, like a uniform error shooting way of or routing protocols. It will facilitate automatic troubleshooting, and we don't have to add additional information on roads, so it will not affect normal routing procedures of existing protocols. And there will be more network-wide data available for individual devices. Next slide, please. So on the previous presentation, we have some feedbacks about our use cases. The use case 1 and use case 2 are already there since the last time. And this time we add a lot more use cases to describe why we want such a protocol and what we want to do with such a protocol. I'm going to start with use case 3. So if we have a peer disconnection issues for either IGP or BGP, RDP, something else, the device that suffers from this disconnection, it could send a request message for the reason. A device that triggers the disconnection gonna say the answer message with the reason of disconnection, including manual shutdown or TCP down or other reasons. Next slide, please. For use case 4, PASP gonna help detecting road interruptions. So road interruptions gonna be very hard to catch for a maintenance personnel. PASP could collecting road change history, and so that rapid road interruptions can be detected, and those data can be fetched on devices that deployed PASP. For use case 5, we're going to have some BGP road no advertised issues. In that situation, a device that suffers from a no advertised situation, it expects receiving a road from another device, but it didn't. It can send a no advertised request message to another device, and the device could give an ACK message with a no advertised reason, including egress filters, no advertised attribute, and others. So for use case 6, we have a road abnormal situations, just like the similarly to use case 5, it can send a request message with specific IP, and the device that receives this message gonna give a reason code like unreachable, next hop unreachable, outbound interface down, or suppression. Next slide, please. For use case 5, we could face the management protocol fails by itself. So like SNMP or SSH. Under that situation, OEM personnel could load into another devices which connected to the devices he used to want to log into, and send a request message to for the reason for the login failure or another failure code of the maintenance protocols. Also, we could have PASP could help collecting other OEM events like IP address conflict or memory leak. So those data can be fetched upon request from a trusted source, so that OEM personnel can get those informations without checking every single devices. One of the original intention of the PASP is that if you are an OEM person and you want to locate some errors happen in the internet, normally you have to log into different devices and check them one by one to see which one get the things wrong. And with such a protocol, we could log into just one devices and to fetch information from our devices. So it's gonna make life a lot easier for an OEM person. Next slide, please. So also from last time we have a discussion in the mail list says what we want to do is kind of similar to RFC grasp, and that's why we add a section about discussion on should PASP be implemented as a new protocol, or should we use grasp mechanisms to do the things we want. These details are already in the drafts. Please read and give our comments about that. Next slide, please. And that's all. We'll come for more comments and discussion. Thanks.
Greg? Yeah.
Hi, Greg Mirsky, Ericsson. It seems that this is just a query mechanism. There is no notification of the failure to be used this protocol for. So it's only for characterization of the problem, not the problem notification, propagating it through the domain. That's my question.
Yeah, I mean, this protocol is just for gathering maintenance informations on a single device of the other devices. It helps to locate the problem of the internet.
Okay, so in this case, so their assumption is that devices will keep some history log of events.
Yes.
Okay, so what your thoughts about how long they have to keep this?
This could be various depending on the vendors.
Okay, so basically then it might be the query comes too late because there are so many devices and whatever the storage is that's being overrun several times.
Yeah, this could happen. We have to find an equilibrium between getting too much data or getting no data, no K data, right? We have to deal with this kind of situation.
Right, because it seems that then the alternative would be to use some notification method.
Yes, we have such a notification message, like we introduced in the draft for the use case 2. So if you have a terminal setup failure, a notification going to be sent upon the failure point to the head point. So there will be some pre-configured situations that says if this happens, send a notification to me. And the more details about this are in the draft.
Okay, thank you.
Ajahn?
Yeah, Ajahn from Chatham. Currently we know the protocol failure by the protocol itself. So I think if we design a general maintenance protocol, each device in each device we need also the interaction between the protocol and the original protocol and the ERP-ASP protocol. So I think what's the efficiency or what's the benefit to use the traditional protocol diagram video? Yeah.
So for the past protocol assisted protocol, we don't have to keep a TCP connection. We use UDP for that. So it's a connection on request. So once you need this information to propagate or you want to fetch the information, you start to use a UDP. That in that way, you don't need to keep you keep two connections all the time. You don't need to do that. Is that your problem?
Yeah. So each failure device will store the reason why the protocol cannot be working. So in your design you just said if we want to know the reason of the failure, we can use it. If we do not want to know the reason of the failure, we need not active the PSSP protocol.
Yeah, it's due to configuration.
On demand protocol.
Yeah.
Okay, thank you.
Adrian.
Hi, Adrian Farrell. You cited RSVP as one of your example protocols you might use this on. Did you mean RSVP TE or RSVP?
RSVP.
Okay. So it might not be as applicable to do this to a connection-oriented protocol like that because mechanisms already exist in RSVP TE for collecting and propagating fault information. For example, 4873.
Yes, just like I said in the slides, a lot of East-West approach have already existed. What we want to do is to gather those information and use a single general protocol to pass this information. That's why in that way, it could facilitate some automatic troubleshooting issues. So if you do that protocol by protocol, it's really hard to gather them together and do some automatic analysis, if that's your problem.
Please continue the discussion online.
Okay.
In the list. Yeah,
Thanks.
You. Dimitri, is this going to be online or?
It is online.
Here. It's online. Okay. Okay. You should have control of the slides. Yeah. Go ahead.
Yeah, and control for the slides. Yeah, I see it. Thanks. So I'm going to talk about routing in Dragonfly topologies and a little bit about advanced topologies for data centers and why we want them, what are problems using them, and so on. It's a collective effort, and intention is to produce at least one document describing recommendations and best practices to make it work. Because we have some prototypes and they're working, and also to start discussion about some advanced mechanisms required to make those topologies really efficient. So what are we talking about, and why would we want new topologies for data center? Usually it's a number of things. It's We want to shrink network diameter, reduce number of links, especially long links, which are expensive, and reduce corresponding costs. We want better scalability. Usually that means that from the same number of switches and interswitch links, we can make larger networks. And also another argument is better path diversity, which usually means graceful degradation in presence of failures. Many or even most ideas for some interesting and advanced topologies originated in the world of HPC interconnects, and now some of those ideas are slowly percolating into the IP Ethernet world. Big problem is that we don't really have the same mechanisms which HPC people have. Things like virtual channels, credit-based buffer allocation, and proper adaptive routing. Here is a link with some good presentation about history of the interconnects, arguments, why we want them, and so on. So next slide. And really, there is a lot of interesting things happening around advanced topologies, but mostly in academic research. If you look at the program of NSDI and SICOM conferences, usually every year there is something new about new, nice, shiny, and advanced topologies for data centers. Many of them are interesting. But most of them are not really deployable, and problems are that they're difficult to expand or deploy incrementally. Some of them have really complex wiring rules, and you need to evolve like group theory to figure out connection between devices, and it only works for particular sizes and so on. They might have nice properties, but it's very difficult to use in real world. Some of the proposed topologies are irregular, and the worst offender is jellyfish, which is randomly connected topology. But some of the topologies are easier to make work in IP world, and they're deployable. Important note is that all of those topologies have common properties. They require more complex routing and forwarding than what we usually do in IP network, because most of the capacity in those networks lays on non-minimal paths. So we need routing and forwarding, which can work for non-minimal paths. That usually means more forwarding state. And to make those networks really efficient, we need adaptive routing, some form of it at least. And one of those few advanced topologies which are deployable and actually deployed in real world, mostly in HPC world, is Dragonfly. Dragonfly is a hierarchical topology which includes several groups, or we can interchangeably call them pods further in the presentation, and full mesh connectivity between those groups. Intergroup topology can be actually any topology. And so the idea is that we have groups, we have full mesh between groups, we have some topology inside groups, and different intergroup topologies produce different flavors of dragonflies. With different, sometimes sufficiently different properties. Focus of the topology and this design is to reduce the number of, first of all, long links, because long links are actually most expensive parts. And also to shrink diameter, to both reduce cost of the network and actually to reduce latency, because if you have smaller diameter, you usually have at least a little bit smaller latency. And topology has maximum 3 hops. And of course, for efficient operation, it requires adaptive routing. Important note, those 3 hops are what they call hops in the HPC interconnect world, where they have virtual channels. So when we translate it into the IP language, each of those hops could be several hops, actually. So that's figure from original paper about Dragonfly topology. So yes, we have several groups. We have some intergroup links. We have endpoints attached to those routers, and we have global links between groups. Idea is essentially that instead of having using just radix of single switch router, we combine a number of global links coming out from the group, and that essentially becomes radix for entire group, and it's much larger than what we can have with single device. And that means that our network can grow very quickly with reasonable device radix, because 40, 60, 80, that's something not only achievable, that's readily available now. 128 radix switches are available. And routing in Dragonfly, as I mentioned, uses 3 hops. One global and 2 local, but that global hop could be minimal hop along the minimal route, or it could be non-minimal, which goes through some intermediate group. One useful visualization actually, if for people who used to work with fat trees, claw topologies with 2 spine levels, what we actually do is that there is a group, and then we kind of reflect traffic from other groups. So other groups behave like top-level spines. And one of the varieties of Dragonfly is so-called Dragonfly Plus, which specifies particular topology for groups. It's full bipartite, essentially leaf spine. So each group is leaf spine and 4 mesh between groups. As far as I know, recent deployments of Dragonfly is usually Dragonfly Plus. But there are sufficiently different types of Dragonfly Plus depending on if every spine in every group has direct link to every other group or not. It could be called like sparse dense, but we really mean sparse dense mean different things for graphs, so it's not useful terminology here. But idea is that either from every spine we can go to every other group, or we need to pick particular spine to go to some particular group. So one topology is on the left and another one on the right. Topology on the right is where not every spine has direct link to every other group. Why would we use such topologies at all? The reason is that if we such a topology, group effective group radix is much higher, and that means we can make much larger network from the same devices. But unfortunately, paths in such a network are not nice, and it's very difficult to make them work with what we have in IP world. Here is what we have for minimal paths. On the left, if every spine in every group can go to every other group, it's very simple. Leaf in some group can go to any spine in its groups, and this particular spine can go directly to the destination group and then go to destination leaf, assuming we don't have failures, of course. But with topology on the right, situation is different. We have to pick a particular spine to go to the destination group via minimal paths. and there is only one minimal pass. On the left, number of minimal pass is equal to the number of spines in the group. And it's not that I like pentagrams so much, it's just minimal non-trivial topology where we can show situations that happens when not every spine can go to as a group. There is another set of paths, which is minimal plus one hop. Once again, on the left, it's more or less uniform, symmetrical, and what's expected. On the right, we can see that there is only one minimal plus one hop pass. It goes through one of the intermediate groups, which is expected. And then yet another set of paths. We don't really need them in topology on the left, but in topology on the right, half of capacity uses such paths, and there learns minimal plus 3. They all work the same. We go to some intermediate group and we to some ingress spine. Unfortunately, we can't go directly to the destination group from that spine. We have to go down, reflect from leaf, and only then we can go to the destination group. So problem is that in transit group or in transit pod, ingress and egress devices are different. And so we have to reflect via leaves. And those minimal plus 1 and minimal plus 3 paths are sufficiently different because with minimal plus 1 path, distance to the destination at least doesn't increase along the path. It either stays the same on one hop, and on all the other hops it decreases. With minimal plus 3, there is hop where this distance to the destination actually increases. And to make it work with such paths, we need proper source-based routing with all-at-once forwarding decisions on the source. Another nice property of Dragonfly, where every spine in every group can go directly to every other group, is that we can decompose the transit links between groups into planes, which is easy to understand, easy to work with, easy to isolate fares. So it's just a nice property which makes it easier to work with. And of course, it's up to permutations because it's possible to rearrange links in such a way that it's difficult to see spines, planes there, but why would we do that? And if we only consider minimal and minimal plus 1 paths, we can make it work with VRFs. We use separate VRFs for intragroup or intrapod routes and for the core or transit links. And in the core VRF, we only install minimal routes. In the pod VRF, we install minimal intrapod paths, and we do eCMP or weighted CMP toward other pods. Google had a number of really good papers describing them current data center design, and they're also mentioning using VRF to prevent loops in topology, which looks very Dragonfly-like for me. So it looks like this. We have like core VRF and VRF in each pod, and on the VRF side, we install multiple next hops for the destination in another pod. But in the core, we only install minimal paths. That means that we first do load balance toward other hop, other pod, but when traffic comes to some intermediate group, it only uses best paths like minimal paths, and there are no cycles in the core. In addition to non-minimal forwarding, we of course need non-minimal routing, and the easiest choice is to use BGP because BGP policies just allow to implement some additional logic which will take into account our network topology. What we do is we do some simple counting scheme to limit the number, how many times our nonsense can be propagated inside the core, and also we remember that. So we add one community when first sending a nonce into the core, when we propagating, we add in another community, and if we see that community too, we don't propagate it anymore. And when we import that into the pod VRF, we just trying to make routes with minimal routes with community C1 and minimal +1 routes with C1 and C2 eligible for eCMP or weighted CMP. We either do ASPAS prepending or just rewrite ASPAS completely.
Dimitri, please
yes.
wrap up quickly. Yeah.
Sorry?
Please wrap
yeah.
up quickly. Yeah.
Yes, I'm close to that. So what we achieve at this moment is we can make this topology work. We can do eCMP or weighted CMP from pods to other pods, but that's not what we really want to do because eCMP or vCMP doesn't really describe properly what we want to do because we want to use minimal paths first, and once minimal paths are filled, we want to start using non-minimal paths. And if some congestion occurs, we want to dynamically shift traffic to other paths. And for that, we need some form of adaptive routing. To make adaptive routing work, we need some long-lived artifacts like flows, because if we don't have long-lived artifacts, there is nothing to shift. That means that easy to implementable schemes like spray and per packet load balancing don't really work because there is nothing to move there. They cannot adapt. Adaptive routing, there are two forms of it. It's global, like end-to-end, based on price properties, and local, which is usually based on queue occupancy. It's supported on many new devices, but it is of limited use because it doesn't take into account global state of path. Important note is that global adaptive routing is reactive because for any reasonably sized network, we cannot have up-to-date information. RTTs in modern data centers are small. It's on the order of 10 microseconds. We have tens of thousands, hundreds of thousands of links, and situation can change on the order of few RTTs. So that means propagating hundreds of thousands or about a million parameters with 10 gigahertz or higher frequency. It's not feasible, but it's possible to make form of adaptive routing with ECN and flow labels. ECNs to detect congestion, flow label to have something to move traffic to another path. There are some problems with ECN, but it's better than nothing. And important note is that this flow label, if we have react on ECN in one of two ways, we either can change congestion control parameters or we can change flow label. That means we will pick some other paths randomly, and it's totally fine because statistically, if there is a congestion and it persists for some time, we will move traffic away from congested paths to less congested paths. And as I mentioned before, we cannot really have up-to-date global state of queues anyway. And once again, at SIGCOMM, Google described similar mechanism. So open questions for adaptive routing with ECN and flow label is how to make a decision when to shift or when to adjust congestion control, how to adapt quickly, minimize rerouting, and all the other implementation details. And it's really a cross-group work because it involves both congestion control, transport protocols, and to some degree routing, because this scheme is useful for particular type of topologies with particular type of routings. And that's all.
So,
Tony?
Tony? Yeah.
Tony P. Juniper. Hey, Dima. I was
Hey.
looking very much forward to this presentation since this is the ongoing conversation we had over the years, right? So, I mean, what I'm reading out of that, okay, you can do this add path BGP, which will cost, massive path hunting on larger topologies. You need this tunneling. What you show me is the conversation that we had. If you want to do dynamic routing on it, it's basically a broadcast domain. You have any topology failures, you have, bandwidth asymmetries, you have to shove it off everywhere and people have to react. So dynamic routing will be too slow for it, right? So that was the discussion about dragonflies we had, a couple of times. The shifting the traffic based on congestion and indications along the paths is a viable thing, right? But it's not dynamic routing. So that's a discussion which is outside of the realm of building a routing protocol that can actually keep up with Dragonfly. Is it doable? Yeah, I mean, look at really old work called DAR, Dynamic Adaptive Routing, which basically what it was doing, it basically remembers whether the traffic went through or had troubles. And based on that, each node basically starts to reshuffle where the flows go purely based on statistic, what was successful, what wasn't. It works stunningly well, right? If you don't manage to distribute the topology information compute based on that, which, I mean, all your presentation was basically confirming to me when I was looking at dragonflies and grow big and you have to tunnel and shorten to these 3 paths and then you start to hunt and every time something changes, you have to broadcast it all over the place and recompute. But the approach of actually reactively just look at congestion stuff and how successful you were throwing something off may work depending on how dynamic your flows are, right? If you have tons of flowlets that shift all the time, that probably, nothing will keep up with the frequency except an out of band control or something like that. But great press, thanks, man.
Thanks. I just want to mention that in this particular scheme, we don't really use tunnels. We are using VRFs, and yes, routing and shifting flows with flow labels are complementary mechanisms because routing going to work on sort of seconds, and adaptive routing can work on sort of milliseconds or faster.
Well, I mean, I can make adaptive routing in milliseconds, but just not as a broadcast domain. That was always the gist of discussion, right? That it becomes amorphous, right? That you have to control where the state is, how much state you redistribute. And sorry, everyone, it's cryptic, right? But this is a very long ongoing conversation. Thanks.
Tianji.
Tianji, China Mobile here. Good work, but this remind me of some implementation that being done like 10, 15 years back from a Brocade on the VCS cluster with a very similar topology as you described here. They can do layer 2, layer 3. For layer 2, they are based on the trail. So have you ever analyzed? By the way, it's being acquired by Extreme. So this one is kind of similar to the work done by Brocade, which was acquired by Extreme 5 years back. Thank you.
Yeah, I provided some links, and Dragonfly is an old idea, like quite old. It just, we are trying to bring some good ideas from HPC interconnect world and make them work with what we have in IP world.
So we'll take further discussion on the list. Practically, this work is really cost and what's been happening in the world over the last 6-9 months. The machine learning networking is really going over the top and it's becoming very relevant. And I think IETF should be looking into better routing, different routing. So that's really the intention of this work.
Thanks.
Thank you.
Thank you. Sorry, I messed up the presentation sequence a little bit. So that was supposed to be number 6. Now we have the tactile traffic engineering.
Colby?
Can you guys hear me?
You should have control of the slides now.
Yep.
Okay, thank you.
Go ahead.
I guess good morning or good afternoon, everyone. I'm going to do a short presentation on our tactical traffic engineering proposal on behalf of my co-authors. I think Tony is on the line virtually as well. So conventionally, we have leveraged, well, this is typically done through RSVP or escalating demand along paths that avoid congestion. This is generally done on the order of minutes. And in many instances on today's networks, either unforeseen or dynamic events like next hop changes can skew those estimates fairly significantly. And this can lead to like suboptimal usage of the resources on the network and potentially unexpected network congestion. So we propose a solution that has a number of different moving parts to avert the detect the congestion in real time, move some traffic around to avert the congestion, and then sort of unravel the tactical nature when congestion has been abated. And there's, I guess, 5 parts I'm going to go through in the remainder of the presentation. How do we characterize and recognize congestion? How do we move and affect the flows on the network through the use of either backup paths or backup fib entries? How are those fib entries activated and subsequently deactivated? What do we do about potentially mitigating further downstream congestion? And then how do we select flows for this type of activation or deactivation? I'll go through them one by one. So recognizing congestion, when a link is nearing congestion or when congestion has been abated, we propose relying on periodically sampling the utilization of interfaces on a local node. The boundaries of this acceptable utilization can be defined by high and low utilization thresholds. And to avoid any kind of oscillation, a link would need to be outside the acceptable thresholds for some consecutive number of periodic samples. There are several mechanisms that exist today that are widely deployed on most modern networks, things like loop-free alternates or facility bypass tunnels or topology independent LFAs. And the key property of those backup tunnels is that they are loop-free and they avoid the primary outgoing interface. This TTE proposal makes use of those backup paths by turning them into an active path when the congestion threshold has been crossed, and then this subsequently creates a equal cost multipath to begin load balancing traffic over the primary next hop interface and then these potential backup tunnels. The TT manipulates these traffic flows by directly activating and deactivating forwarding information, fib information, and forwarding information, base information. Activation is what we tend to talk about, and when we select a flow, we make the appropriate data plane changes. So it's said to, the TT is said to be activated. Deactivation, of course, is equally important so that we can undo whatever spreading or ECMP has been activated in the network when the primary path's utilization threshold goes below the low threshold. Any downstream congestion, while we have thoughts on mitigating potential sequential activation of TTE tunnels, There's a sort of base assumption in this proposal that any network that is using backup tunnels, whether they be TLFA tunnels or facility bypass tunnels, has done some sort of proper engineering to support that protected link against catastrophic failures. So in other words, it's we assume unlikely to create further downstream congestion because the network has already been engineered to sustain at least a single link failure. When the link sort of crosses these bandwidth thresholds or these utilization thresholds, we need to be able to select some number of prefixes to activate or deactivate in the case of congestion abating. And the draft, I won't go through them here today, but the draft describes briefly several different methods for selecting prefixes to activate. We can do random selection of all of the prefixes that have a primary next hop that is under congestion. You can not select elephant flows, try to only move around mice flows, do maximum fit and best fit techniques, or maximum fit with elephant flows. All of them are briefly described in the draft. And I believe that's it for me. Questions?
Hi,
You guys still hear me out there?
Vladimir Erickson. So, yes, a couple of questions. So first, as I understand it, this is to be monitored on a link level, not on a path level. Okay, so their detection of congestion happens on an egress of the downlink of the link, and their action is supposed to be taken by the ingress, so the upstream node.
The action is taken by what would otherwise be the point of local repair in the event that we're using existing backup tunnels. So if congestion is detected on an outgoing interface of a node, that node also serves as the ingress for any local repairs that need to be done for that outgoing interface. So it would be a action taken by the point of local repair, not by any upstream nodes.
Oh, so basically you monitor the outgoing interface, not incoming interface, and then you take action. So basically it's not incoming queuing that you monitor, but your outgoing queuing that you monitor. I see. So, and that you don't take into consideration of traffic that comes to this node and congests this.
We don't take into consideration sources of the tunnels or sources of the traffic that are coming to the node, but all traffic coming to the node is under consideration for any interface that's monitored for this congestion protection.
Okay. Okay, and because their action is local, so their effect on overall other flows cannot be really considered.
Yeah, I mean, only flows transiting that node would be under consideration. Yeah, so we're not trying to make a global repair decision. The goal is to do something locally fast while global repair goes about its normal business. So.
Okay.
Right. Okay. Thank you.
Himanshu, you are the next. Are you in the room or remote? Please go ahead.
Can you hear me?
Yes.
Yes. Yes. Okay. So this is, as I understand it, briefly, I haven't read your draft, but it is doing TILFA on a congested outgoing link, or sometimes what we call is on a signal degrade. Here signal degrade would be the congestion, doing a protection switchover type of things that has been well known before. Now, my point here is that isn't this a local implementation? It's an implementation specific. It's not like it requires an interoperability and it needs that IETF work to interoperate with other devices and
That's
stuff like that, right? Is this just an
Yeah, this is
informational
just an
draft? Or?
informational draft. You're absolutely correct. It's a local implementation.
Okay. Okay, so I think is it all right as long as this is informational, probably nothing required for interoperability, because I think it has also implications on, well, you switch over to the TILFA or backup paths, then what happens to the traffic that is already ongoing on those links, right? You have to have some sort of a network view in order to intelligently decide whether you want to overburden the other links or not. You may create problems somewhere else, right? It's a kicking the can up
Yeah.
to
So
some
I
other area,
believe
right?
in the draft we briefly talk about different mechanisms for computing these like TTE tunnels, I believe we call them. I used the TLFA example in my presentation here, but there are other mechanisms for calculating backup tunnels that can be used, or TTE tunnels rather. Yeah.
Right, right. I think in an end-to-end cases, the backup tunnels that are pre established and are engineered, so it is better to switch over to those rather than doing TLFA or anything like that. Anyway, you answered my question. Thanks.
Yeah. Please be brief.
Okay. Zheng Bin from Huawei. My question is that I'm not sure I understand this one or not, because I want to, because this is the traffic engineering, so that is change the path end to end, or is change this locally. If it's change locally, is it will it cause the out of order of packet forwarding?
Not 100% sure I understand the question, but are you asking, will this cause out of order packets?
Yeah, I mean, so that's because you this is because the path is changed, but you know that the beginning the packet is forwarded in order, but because the path changed, so that is maybe
Yeah,
out of
so
order. I'm not sure.
Typical, hashing across equal multipaths does, it is flow based. So because we're not randomly spraying traffic across the ECMP that we've created, but continuing to do flow based hashing, I don't believe there'd be any packet reordering problems.
A more significant issue is that you're going to have a delay change, and that may trigger slow start. So there is a performance impact.
Okay.
I'll be quick comment from my side as a participant. There's technology called adaptive routing and DLB. It's somewhat similar. It looks into occupancy of outgoing queue and distributes traffic differently. It suffers a lot because of its locality. So having better understanding of what downstream of you might make your solution much better. I understand it's very simple, it's local implementation, but it really suffers, and you potentially might send traffic into congested downstream device. Even so, as you said, you consider that it's well engineered, in many cases it isn't. So maybe adding some non-local signaling on top might increase your solution significantly.
Thank you, Jeff.
Hello, hello everyone. This is Haibo from Huawei. Today, I'll present a topic about the two jobs. It's the requirement and the framework of fast fault detection for IP-based network. Next slide, please. Here is the agenda. First, we'll recap our solution, and then we may see the discussions from last meeting. Next, please. Here is the motivation for our solution. Today, most IP-based applications always use the keep alive mechanism to identify network failure. But also they want to fast detection for when the network is failure. Especially for the high performance applications such as IP-based NVMe and class computing, they can't tolerate the long duration for failures. Although there are many mechanisms now, such as BFD, we can deploy the BFD to detect the failure. But these mechanisms typically may consume more system resources. So for IP network, we want a mechanism to help the endpoint to accelerate the fault detection and can make better experience for these high performance applications. Next, please. Here is a use case. It's a scenario for IP-based NVMe. When the host and the storage are connected to the IP network, when the host creates a NVMe connection to the storage device, when the storage link is failure, the host NVMe connection will not work until the keep alive timeouts. This may be duration may be about more than 10 minutes, 10 seconds. Next slide, please. This is another use case for distributed storage scenario. In this scenario, the distributed storage devices are connected through a backend IP network. Also, when the storage device connection link maybe fails, the master node cannot detect this until it's the timeout, the keep alive timeouts. Then the master can switch the service to another storage device. It's also maybe the duration may be about more than 10 minutes. Next slide. This is a use case for the class computing. It's similar to the use case 2. Here, there may be a job scheduler to reschedule the class computing. They may this here it divide the 4 servers into 2 pairs, so one server 1 to server 3 and server 2 to server 4. One server 3's link maybe fails. The communication between the server 1 and server 3 may be done, but the whole computing is continue doing. But the job scheduler cannot detect that. So cannot detect that. But the whole class computing may be interrupt until the job scheduler detect this failure. It can then maybe do rescheduling about the whole computing task. It also may be the duration may be more than 1 or more minutes. Next slide, please. Here is our expected framework. This framework will run in a limited domain. For here, the client endpoint or the server endpoint may also connected to the IP network, and they may register their information such as their role, their IP address to the IP network, and they also may subscribe to the network for which information he wants to know. the IP network will synchronize these informations through the IP network devices. And when the IP network device detect some failure, detect the failure for some link failure or on convergence network failure, it will synchronize this to other devices, and then it will notification to the access the endpoints where the failure has occurred. When the endpoint device receives that notification, it can decide how to do next. Then they can do fastly service recovery. So we can accelerate the whole failure for the whole failure. Next slide, please. This is a procedure sample for IP-based NVMe. The host one connects to storage one through the IP1 and IP2. When the and firstly, the host and the storage all register their information to the IP network, and the host one may subscribe to the switch. He wants to know the IP1 and IP2 the status. When the link from the storage one to switch one fails, the switch will notify that the failure to host one because he's interested in it. Then the host one receives the notification. They can do fastly recovery, so the service can be infused in very small minutes. Next, please. This is another procedure sample. This is for class computing. This scenario is similar to distributed storage network. Here, the 4 servers are divided into 2 pairs. Also, the server 3 the link is fails. The failure will be synchronized through the switches, so the leaf 1 can receive this notification, and he will notify it to the job scheduler. Job scheduler receive this notification, then they can judge and do the task rescheduling to ensure that the whole computing task can be continue correctly. Next slide, please. Then we may see some discussion from the last meeting. It had presented at the IETF116 before. Here is a comments by David Black. He means that for NVMe over IP NVMe over Fabric, the active mode is usually used. So when one pass fails, the storage device can notify the host through the other pass. Yes, also it maybe works, but in this mode, the storage device can only detect the local link failure, such as the storage device to the switch. It can detect it and notify it through another path. But for the storage network, there may be also some failure, not only for the access link, such as the link between the switch is fault, and this fault cannot be converged by the IP network. So the storage device cannot detect it. So then the mechanism cannot work. Next, please. Here is another comment by Sasha. Because as the topology we showed before, this means that this may be a port network like the topology 1 here. Should we avoid such a failure through the network design and prevent the device from sensing the network failure? Here also we may show some other topology like the topology 2 and the topology 3. This can support more higher reliability, but the storage network is often a small data center network. And also sometimes the customer wants independent dual plan design. So for the topology 2, it's also with high ability, but in customer's opinion, it's not support the independent dual plan. And for the topology 3, it may be both satisfy the higher reliability and also can also have independent. They are also strictly independent, strictly independent zero plan. But this topology will cost more construction cost, so it's not also not satisfy customers' requirement. Next, please. Here is some comments by Jeff. He means that for machine learning cluster, the goal is to detect a failure, a sub, and route it in IP network. This is commonly implemented on the host today, like a flow bender or a variety of other techniques. Yes, there are many communication framework now can be used for the high performance computing. They also can support some quickly failure detection. But these faults cannot be resolved all the failures, also such as the IP network failures. So when we support a mechanism from the IP network, we can detect the failure and notify it to the job scheduler. Then the job scheduler can judge. They can judge and how to do next. So they can maybe do rescheduling and other process. Next. Here is also comments by David Black. He means that we he thinks that perhaps we have missed the security consideration chapter. Yes, we have considered it in the description. We have introduced 3 types of messages in our solution. The subscription message and the notification message only run between the endpoint device and the access switch. This message will not run out of the range, and also the switch will not forward these messages, so it's safe. And also there is another type of message, synchronization message. This will be run between the switch network, IP network based device. This message is running based on the TCP and quick. These transport protocol also have safe and reliable methods, so it's also be safe. Next, please. This is some comments about from Greg and Tony Lee. He says they think that our solution is similar to the UPA working in LSR. Yeah, the UPA working in LSR need to do extension on IGP, and but they only transmit the IP reachability information. In our scenario, we also want to do collaboration with the endpoint side. We want to collaborate with them about the subscription message and the notification message. IGP extension can only be used between the IP network device. But this is also a choice. But we also want to consider more general scenarios, such as because for data center networks, not all data center networks run IGP as a protocol as an underlay protocol. Next, please. About these discussions and some consider, we have updated our drafts. We have give more detailed description for IP-based NVMe scenario, and also give more about the class computing scenario. And we complete the security description chapter. And last, we optimized our description for the framework document. Next, please. And also, at last, we welcome more comments and discussions, and also we welcome join us. That's all. Thank you.
Greg, please
Yes,
speak.
Thank you, Greg Mirsky Erickson. First, the comment, the question about the terminology you use. The mechanism that you described doesn't seem to be a failure detection. It's more notification. So As I understand, you use some other mechanisms like BFD that you mentioned to detect the defect. So everything here is described and explained is propagating this information through the management plane.
Yeah, and we said before, because other mechanisms such as BFD maybe let the endpoint system system resource more heavy. So we don't want to run it on the endpoint, especially for some server endpoint, such as the storage. It will be maybe connected by too many hosts.
Greg,
Okay,
maybe
so
can
you mentioned that what's the problem, the motivation for your work is that the discovery is in terms of 10 seconds.
This is this is according to the keep live timeout set because for normally for IP-based MME scenario, most of the time the keep live will be set to 5 minutes. So it's so when it detects the failure, it will cost about 15 minutes.
Okay, yes,
seconds.
that hints me, gives me an idea that probably it's not using some OEM mechanism like BFD to do fast detection and fast conversion in IGP. So it seems that it's not really a good design. Thank you.
Okay, thank you.
Zhenbian from Huawei. My quick comments is that it seems to have some relation with the CAS working group. So I hope that you can do some of the coordination.
Okay, thank you.
David, please go ahead.
Yes, first a quick correction if I broke. You actually misspoke. The failure detection times are measured in seconds, not minutes. So the keep alive timer you're looking at is the 5-second timer. It's interesting. Response comments from the last meeting. You're now looking at unconverged network failures. How do you detect that a failure is unconverged?
I'm sorry, I can't hear it very clearly.
Yeah, I think your voice is breaking up a little bit, at least for me. Can you please repeat your question?
Okay, the question is, for an unconverged network failure, how do you detect that the failure is unconverged?
You mean that how to detect the failure? Yeah, because we are do it.
No, it's not how to detect the failure. A link has failed. How do you decide whether the failure is an unconverged failure or a failure that has been converged?
I'm sorry, I'm not. Okay.
Unconverged.
Okay, let me suggest
Yeah,
the problem.
The unconverged failure is according to the topology because we may see the slide about 7 or slide 7. Before one. Oh no. But next one. Next one. Discussion page 1. About 9 page 9. Yeah. For this topology, when the connection between the switch, such as the left side, the link fails. It cannot be convergence because they don't have yeah.
This is a very simple example that looks fine on slide grid. How would you do that for the Dragonfly topologies that you saw earlier in this session?
Yeah, because next slide, please. Next slide. Yeah, also we consider that the topology may be very kind, but also here the topology 2 and topology 3 can support more higher reliability. But the topology 1 it also exists for some customers. They want only independent dual plan. So the topology design here is maybe seems like a poor network, but also it exists.
Oh, I know topology one exists. However, I think you're using very simple examples where it's obvious when a failure is unconverged. And it sounds like you're planning to construct your own network topology independent of what routing protocol does. And it doesn't sound like a particularly good idea.
Okay, I'm sorry, I'm not very clearly understand your question.
David,
Okay.
maybe you can look at
I'll
the
take this.
meeting minutes.
Okay, okay.
Yeah, I'll send an email. That will be better.
I'll take
it to the list.
Make
Thank you.
sure the meeting minutes catch your question
Yes,
correctly.
I can end the minutes and take it to the list. Sorry, the audio's not working well.
Thank you, Hepo.
Thank you.
Mhm.
So we may not have enough time for the GIP6 presentation, so sorry about that.
Okay. Okay, so this is Jimmy. So this is a quick update about the APN work. Okay, next page. Okay, in fact, this has been presented in the IETF 113. So that's this work began in the in March the 2019. So that's after that is many set meetings and also have the both. Okay, next page. Okay, so this is just last year this summary. So this is the first that's the 113. So that's the closure the issue proposed in the APN BOF. And so then that's is a recommendation for the focus working group according to the rough consensus in the RTGWG. So that's the first. So then this is 114. So that's is agreed to move to the focus working group by the IETF 115. And then that's is when the charter is proposed, it has blocks from the ISG. So that's is the proposed working group meeting was cancelled. So that's is also the response ID suggest had another BOF. And so then this is the 116. So that's the is the proposed working group process is reset. So that's is so this is the process. Okay, next. Okay, so in fact, after the IETF 115 and the 114 and the IETF 115, so that's is we have the several rounds the refining the charter and to make it more specific, and also thanks to the comments from the different parties. So that is also based on this the refining. We try to make this problem statement and scope that is more concrete. And also that's extensive this communication with the IESG members, operators, and the vendors. So and also is to understand their the concerns and also clarify the scope and also the on the issues of privacy or the network security. And also this is to enhance this the understanding each other. And also, that is unlucky that the APN work is being done in the past 4 years. We have the 3 years is the 3 years is the COVID-19. So that is also is affect this efficient communication. And a second one, and because we are is waiting for the process, so that's the refinement of this the use case or the problem statement is stuck. Okay, next page.
Robin, you've got 2 minutes to finish, so come to the cheese.
Okay, yeah, it's done. This is the last page. So that's this is the feedback, yeah, from this one. So the first one, that's the more valuable use case to justify the scope and the value of the APN work, and also the more diversity of the participants. Okay, I think that is good. So that is according to this the extensive communication. We also had more idea about this the use cases and the problem statement, and also that is also more participants would like to join the work. So that's the next step. We will have this a plan to set up the virtual design team to work on this the use case and the power statement, and welcome to join. Okay, thanks.
Thanks, Robin, and we are on time. Joel, last comment.
Joel Halpern. No prejudice to your presentation just now. Presentations of side meetings that are not chartered work, and we're not even seeing the work, you're just summarizing what you were trying to discuss, do not seem appropriate for this working group. And the next one that's on the agenda seems to have the same problem. I'm no prejudice, as I've said, I'm even willing to help you guys try to get to a problem statement that we can actually progress on. But that doesn't mean it should be presented in the RTGWG. And I'm just a bit frustrated, not with you personally, but with the structure.
Okay.
Thanks, Joel. And point taken. So we are on time. It's 7:30 in California. So thanks everyone. Thanks David for taking the notes, and we will see you in San Francisco.
If you said anything at the mic, please make sure the notes are correct. I had some trouble keeping up.
Okay.
Thanks everyone.
Okay. Thank you everyone for attending the meeting and have the good discussion. We'll see you in San Francisco.
Safe travel back home.
Oh, you're out now? I have to go, yeah.